Okay, so in this video we'll be going over a sample problem here from the early stages of Chapter 2. Chapter 2, the main focus, or the main goal here is to look at fluid statics. But to get there we have to introduce the idea of pressure and be very careful with what pressure is and how it plays a role in fluid systems. So this problem here deals with atmospheric pressure variation. So let me first start by just showing what's in the book. 215. We're not doing the giraffes, but here's 215. Just much more boring. Just a paragraph and some data. No giraffes. But so what this says, the paragraph is basically saying that normally temperature decreases with elevation as you go up in the atmosphere. However, there are some situations where you can get temperature increasing as elevation increases, and so here we have, you can imagine a big mountain with a bunch of sensors along it, and all these sensors are measuring temperature, and that just spits out some data. And let's do something with this to tell us about the pressure. If we know the pressure at the base, tell us the pressure at the top of the mountain. So here's my retelling of this system. Determine the pressure at the mountain top using numerical integration, and we'll get to what we mean by numerical integration of the temperature inversion data. So this is really what's given to us, and I've just drawn the mountain here is just to remind us, here's the mountain going up, and our data is given us in kind of what you would normally be in the opposite direction. So as we go further down in our data, we're actually going up higher into the mountain. All right, but we can see here that generally as we go up higher on the mountain, we're getting to higher temperatures, which is why this is called a temperature inversion. To use this, we'll see later on, we'll fill these out, but basically we just need to convert this to Rankine, from Fahrenheit to Rankine, by adding 459.67, and then we'll need to do 1 over the temperature in Rankine. And the reason we needed to convert it to absolute temperatures here is so that we can do 1 over the temperature. We can only keep them in Fahrenheit or Celsius if we take a direct subtraction of a temperature, but if we're going to do 1 over a temperature, it needs to be in its absolute temperatures, or in a Rankine or a Kelvin scale. Okay, so to the solution of this, again, we're just going to use this data to determine what the pressure is at the top, given that the pressure at the base of the mountain at 5,000 feet is 12.1 absolute psi. And be clear, psi is pounds per square inch. The A stands for absolute pressure, not gauge pressure. Okay, so we'll start with this by assuming that the atmosphere is an ideal gas, or that air is an ideal gas, and for air it's a pretty good approximation. It is an approximation, but a pretty good one. For other, pure helium acts, purely. There are some that act more perfectly like an ideal gas, but air and most gases in engineering applications it's a pretty good approximation to use the ideal gas law. So that relates the pressure to the density and the temperature, where if it's an incompressible, it's generally a compressible, gases are compressible, so our density can vary, our temperature can vary, and our pressure can then also therefore vary. The R is for a given species of fluid, or for a given gas, the R is a constant, a gas constant. Okay, so we then start with the hydrostatic relationship. Hydrostatic, again, meaning fluid at rest. So here, this chapter is all about fluid statics, and that's basically what hydrostatics means, just fluid statics, or fluids at rest. And that is just that our pressure gradient for a static system is just minus rho times g, so minus density times the gravitational acceleration. So this gives us our pressure variation in the direction of gravity, whereas the pressure variation in the horizontal directions is just 0. So dp dx and dp dy is just 0. Those are our hydrostatic relationships in general. However, this is a differential equation, but we need to write it in this general form, since the simpler forms we have are assume that density is constant. And then obviously if density is constant, this is a pretty easy thing, differential equation to solve. It's just, a derivative over here equals a constant, and just turns out to be a linear profile. But since density is not constant for a gas, we need to be a little bit more careful with it. So again, the fluid property of interest here is going to be this gas constant of air. Let me show you where that is. That's now going to be table 1.7 in our book. Can I get this? What are we in? SI units? We're in, we are in British units here. If we just look at standard air, interestingly enough, we have a temperature given here, but we're just going to use, say this doesn't change very much, this 1.716 times 10 to the 3 feet-pound per slug degree Rankine. Why I mentioned that this, all of these fluid properties do, in general, change with temperature, and our system, the data we're given has temperature changes, right? So you might think that, we have to basically make a little bit of an approximation here that our fluid properties don't change with temperature, which is often a good approximation, but something we should be aware of, because there are definitely cases where extreme temperature changes have huge effects on something like viscosity. Okay, so now we just combine these two equations. So dP dz, plug in what density is, which is just P over RT. So minus P over RT times G. G, R, and T, G and R are going to be constants, but T, now we have how T changes with height. All right, so we have how T changes in the vertical direction in our data. It's given in data form, not in the functional form. But we want to get all the pressures to the same side, so we bring the pressure over to the other side. We get 1 over P dP equals minus G over RT, and then integrate that. 1 over P dP integrated from some first pressure to a second pressure, and where what 1 and 2 are associated with is some different elevations, right? So we're integrating both sides from 2 different elevation points on the mountain, and therefore we have the data at 2 different points. We know our temperature at those 2 points, at any 2 arbitrary points, but we don't know anything about the pressure. That's going to be the unknown. Well, we do know one pressure. We do know that the pressure at the base is 12.1 psi absolute, and then we know the temperature at all these discrete places in between. So we can integrate the left-hand side pretty easily. This is just a natural log of P evaluated at P2 and P1. So this is a log of P2 minus a log of P1, which combining that, we just get the log of P2 over P1. And then we can't do anything with the right-hand side yet. We have numerical data for this, but we don't have a functional form for what the temperature is with the height Z, with our elevation. So this is a good form here to start with, but we're going to need to integrate this numerically. And that means using a software package. So I hope this is a bit of a refresher, that you've seen this before. If not, search do a Google search here for trapezoidal rule. Wikipedia has a nice article on it. Pull out your any book. I just noticed there's a mistake here. And that says we can't have an integral without a differential inside. What this says is that if we integrate some function between 2 points, right, where there's some real relationship f of x, but we don't know it. We just have information at 2 endpoints. We just have the information of the function at a and b. So the function itself has some curvy nature to it, but all we know is a and b. All we know is the function evaluated a and b. So all we know is f of a and f of b. We don't know in general what it is in between. So given functional data at 2 points, we can then well approximate what the integral is, so the area under this black line, by a trapezoid made up of the 2 endpoints and then going down to the horizontal axis here. So this is x, this is our f of x. Right, and so you can see for this case, it's a pretty good approximation. Yeah, we've undershot the area for this first part, but we've overshot the area on the second part, and they'll kind of cancel. And there's going to be some area here, but it's not too bad. And so what this ends up being, and so the area of this trapezoid is just b minus a gives us b minus a gives us the base length, and then the f evaluated at a plus the f evaluated at b over 2 gives us the average value. And so that gives us the tip, if we make a line of this, it gives us the average value in between, and that, this is the form for the area of this trapezoid. And so that's why it's called a trapezoidal rule. We make trapezoids, take areas of those trapezoids, and then take that as an approximation for the integral. So in general, approximation is improved as we get more data. So as b minus a, the difference here gets smaller and smaller and smaller, our approximation gets better. And then we can extend this to the full integral. So the integral I, a full integral, for many, so in our case, we're given data at many points. We can take each different, the interval between 2 points. So as we go to 2 different elevations up our mountain, we can go to each one and make trapezoids between them and take the areas of those trapezoids and sum all of those up independently. And so all we have to do there is then convert our single interval trapezoidal rule to many intervals by summing over, if we have n data points, we're only going to have n minus 1 intervals. So we're going to sum from 1 to n minus 1, where this is just now taking this form and evaluating it at each individual interval. So we have xi plus 1 over minus xi. That gives us our b minus a for each interval. And then we have the data points. So this would be our 1 over temperature. Well, we're given temperature, but we'll see this will be 1 over temperature, the average of the two endpoints for each interval. Okay, so we're looking to then approximate this integral over our entire mountain, so from the base to the top of the mountain, where the integrand here is 1 over temperature. So our f needs to be 1 over temperature, and that's why we had to go through this very simple data processing to get to 1 over temperature in Rankine. And then our x is now going to be our elevation, or what we've been calling z. So if we want to integrate from the base of the mountain, 5,000 feet, up to the top at 9,900 feet, 1 over temperature dz, there's our integrand. We then, well, this isn't just magic, this 9.3449 feet per Rankine. I didn't just come up with this, let's look at how we got this. But in general, you can use any software that can do, simple, data analysis or data processing. And I'm going to show you both in Excel and MATLAB, MATLAB being my preferred method. So let's start here with the Excel file. I thought I had it open. Okay, so here, this is that data just reproduced in tabular form, but in Excel here. So we have, these first 2 columns were given to us. We've then converted it to Rankine and taken 1 over that, 1 over the temperature. So these 4 are the same as I had written down on my page. This now is our trapezoidal rule. So at every single, let's go to some arbitrary point here. Every single one of these, we take A6 minus A5, so we're taking the difference in elevation, multiplying it by the average of these 2 values, and that gives us the little area here for, the area under the curve associated here. So the area under the 1 over t curve as you climb up your mountain. Go to another one, we're taking the difference of this minus the one before it. That gives us the difference in elevation. And then here we're taking the average of the 1 over t's, between, at those 2 endpoints, and I'm multiplying those 2 together to get this. Sum all of these up, so if we go to the bottom, we're just summing up E3 to E11. Excel nicely highlights that for us, so we're just summing that up, and that gives us, our 9.344869348, which we'll see, and here we have to be a little bit careful what units we're in, but you can work through that. Okay, let me then also show you how we can do this in MATLAB. So that's here. So you can ignore everything from down here. This is just going to be working on plotting and things. And I'll show you the whole file if you want to know how I like to plot things. You can see but everything from here up is all we need to do with the trapezoidal rule. In fact, here is just the data. Here we're given temperatures. Here is my data given in the elevation data, so T and H. Here I'm just taking inverse temperature, or 1 over temperature. It's just 1 over the temperature plus 459.67. So here's the conversion to Rankine, and then 1 over T. So here, this is just 1 over T. Right, so everything here is just working with the data to get it in the right form. So then this, right here, is our trapezoidal rule in one line. And that says, take the sum of little bits of h's, delta h's, so take all of the, hi plus 1 minus hi, where here we're using vector notation, if you're comfortable with that. And then here we're taking 1 over temperature, the I plus 1 to the i's, taking 1 over ti plus 1 over ti, and then dividing that by 2. So here's our average temperature, average of the 1 over t. You can do the same thing with temperature to just get what the average temperature is, and that's what I've done here. So this will give us the average temperature. But this gives us what I is, our integrand. It's hard to see with the orange line, but this is I, and I'm just, big I here is just integrand. And then everything else is just plotting. So if I run this file, we produce a few figures, and I'll look at these a little bit more carefully in a document here. But essentially that integral becomes 9.3449, and the average temperature is 64.7. That's just the average temperature we get in the mountain, and we'll see why we're going to use that here in a second. But right here. So here's a nice little summary of everything we've done. Here's the MATLAB code for the trapezoidal rule. In fact, this here is just the trapezoidal rule. Everything else is just working with the data. So pretty simple. And some plots. So here's our temperature profile. I've just plotted just what the temperature is with elevation. So from 5,000 up to 9,900. We see that we get an increase in temperature going upward, which is what we call a temperature inversion up to our mountain, and then it does kind of backtrack a little bit as we get really close to the top. We then look at the trapezoidal rule for the inverse temperature. Again, that's I've turned this on its side, right? So like typically we think of areas going down to, when we're integrating down to the x-axis, but since we're talking about elevation, I decided to show it this way. So here you have 1 over t on the x-axis, and our elevation is on the y-axis, and we're taking the areas this way to the y-axis. And this is just 1 over, we're just integrating 1 over t. So it's the area under this whole bit. So if here t increases and then decreases, we'll see that 1 over t decreases and then increases up near the top. But these values are so large, the changes in this 1 over t is so small compared to these values that perhaps you could just take the average value here and just sum it all up, which will show us a pretty good approximation. I've zoomed it in here, right? This sums it all the way down to the y-axis. Here I've cut it off so you can see what these little tops look like. So you can just think this is on the right-hand side is just the little segments here left over at the top. But we have all of this additional area added on. So when we're integrating this, we're taking the area that is constant for the whole way up the mountain, and then adding on a little bit more for some parts than other parts. But in general, since it's not changing very much, we could just use an average value, and we'll see that at the end of the video here. So let's go back here. So you can see that using software and our trapezoidal rule, we found this to be 9.3449. Units here are going to be just feet per Rankine. You can see that in our integral. Z has a units of feet, and our temperature is just in Rankine, so feet per Rankine. We then go back to our formula, plug in that the natural log of P2 over P1, or in this case P top over P base, is going to be what do we need? Let's go back to it. So it's the integral of 1 over t between two heights. So that came from our trapezoidal rule, but now we need to multiply it by minus g over r. G is 32.2 feet per second squared. Our r is 1,716 feet-pound per slug Rankine. Noting here, reminding that a slug is a pound second squared per foot. And running through our units, noting that feet cancels, our Rankine cancels. Our slug, if we plug that in, that it's pound second squared per feet, is going to cancel this pound second squared per feet. This is something maybe to to pay attention to whenever you have a natural log. It had better be unitless. So there's no units left over. So the log of the ratio between the pressure at the top and the bottom is this minus 0.1754. Take the exponential of this number to get rid of the log, and multiply over by the base temperature, which is 12.1 absolute pressure, absolute psi. Again, taking the exponential of this not dimensionless number, we're left with 10.15 absolute psi. All right, and so that's the pressure at the top. So the pressure at the bottom is 12.1. We see a decrease in about 20% of the absolute pressure at the top of the mountain from this temperature inversion. So this is where, this is the final answer, and we did everything rigorously and ran through, made sure we noted that density changes with temperature, so pressure changes with temperature, obviously, but so does density for air. But the temperature differences are so small. What if we just use this average temperature? The average temperature is 64.74 degrees Fahrenheit. I showed you in MATLAB how I calculated that, but you could just look at the numbers and just use an approximate value. If you then plug that in, instead of doing the integral with the trapezoidal rule, instead you just say that temperature is constant, and pull the temperature out of the integral, then you just need to do the exponential of g over RT, that constant temperature, times the total change in the height. Right, so here we're just plugging in the delta z is just the 4,900 feet that we have here. So you're just plugging in 4,900 feet, plugging in the average temperature. So we're not doing any integral here, or if we are doing an integral, it's just of the height, and we're not changing the temperature with our height. Again, you just get 10.15 absolute psi. So because the variations in temperatures are not that significant, we're able to just take the average temperature value and use that instead. When, in fact, to be fully rigorous, you need to take the average value of the 1 over temperature, the average value of the inverse temperature. So a fine point, but it's probably good to be careful of this. But the reason that these two numbers are the exact same is that the average temperature is so much bigger than the temperature variations.